Kia ora koutou. My name is Zhiting Chen from the Department of Public Health at the University of Otago, Wellington. So it's my pleasure today to share our work, Summertime Thermal Risks in Energy Poverty in Aotearoa's Low-Income Housing. I was also part of this symposium last year, and I shared some findings on the increasing risk of summer indoor overheating and growing demand for active cooling. In today's presentation continues that story, showing where the new data and projections are taking us. So to start, I'd like to briefly come back to the study I shared last year. So that was a small case study of public housing apartment units in Wellington. In that work, we monitored indoor temperatures in 7 public housing units and interviewed the tenants. We found that some households, especially those without portable air conditioners, were living in uncomfortably warm and at times unhealthy conditions over summer. Because the study was small, we had a lot of questions about how generalizable and representative those findings were. That feedback really shaped the next step in this work, and it led to the larger study I'm presenting today. So in this study, we use indoor monitoring data collected from 4 different research programs and projects, all working with households facing low income, poor quality housing, and/or energy hardship. The data cover 4 consecutive summers from 2020, 2021 through to 2023, 2024. In total, we have measurements from 542 homes across 6 regions in New Zealand, with over 1.6 million individual indoor temperature readings. Most of the monitored homes are in the North Island, with fewer in the South Island. Right. So because we wanted to understand how future warming might shift summer indoor risks, we first built a fairly simple linear model that links indoor temperatures to outdoor temperatures from nearby weather stations. So we included home-specific fixed effects. So each home has its own baseline temperature to account for differences in things like insulation, orientation, and how people use their homes. Then we took the projected temperature increases from the New Zealand Climate Change Projections Guidance and applied those to the outdoor temperatures, which allowed us to generate projected indoor temperatures for each dwelling. In here, we chose 2 emission scenarios. One is SSP 2 4.5, a moderate emission scenario, and SSP 5 8.5, which is a high emission scenario. To assess overheating, we use SIPC TN59. For anyone that's familiar with this, it's a widely used overheating standard, especially in Europe and the UK, for free running residential buildings in temperate climates. So for daytime conditions, TN59 sets a simple overheating test. Indoor temperatures should not sit more than 1 degree above the adaptive comfort temperature for more than 3% of the summer hours. When we applied this, we found that more than 1/3 of the dwellings are already failing this test. So they are already experiencing daytime overheating. And under future warming, that increases to more than 40% of the homes. In TN59 has a separate test for bedrooms, which says the temperature should not exceed 26 degrees for more than 1% of summer sleep hours. When we look at nighttime overheating, the results are even more concerning. More than half of the dwellings already fail this test, which means many households are trying to sleep in uncomfortably warm or potentially unhealthy conditions. That has obvious flow-on effects on for how people feel the next day, their ability to function or work, and for their general well-being as well. Under a high emission scenario, that proportion is projected to increase to around 9 in 10 homes. So nighttime overheating becomes almost universal in this group. So this larger study shows that what we saw in the small Wellington case study wasn't just a one-off. Those earlier findings are actually quite consistent with what we are now seeing across a much bigger sample of low-income homes. While we were doing this study, we started to get questions from policymakers and other building researchers that TN59 is widely used, but how well does it actually capture risk in New Zealand homes? That really made us step back and reflect. and we compare the TN59 results with people's lived experiences from our interviews and case studies. And we started to think, hold on, this might not be a great tool for our context. If we rely on TN59 alone, we're probably understating both the heat risks and the likely energy, the energy demand during summertime. So first, TN59 is based on seasonal criteria, like no more than 3% of summer hours. That means short but intense periods of heat exposure can be masked. But those short heat events can be extremely dangerous, as we've seen with heat waves in Europe and other cooler climates. In here in Aotearoa, we are already seeing more of these hot spells, with more to come under climate change. Second, the standard is purely temperature-based and assumes indoor relative humidity is in the optimal 40 to 60% range. In New Zealand homes, we all know that is often not the case. They tend to be much more humid. So high humidity is a health risk in itself, and it also increases heat stress, making conditions feel much worse than temperature alone would suggest. Third, the summer TN59 test really only looks at high temperatures, which makes a lot of sense in many climates, but it doesn't fully fit ours. New Zealand has a long heating season, and in recent years, we've also seen some quite cold days even within the summer months. So when you combine that with low thermal performance in much of the housing stock, you get the potential for dual exposure to both heat and cold in the same homes within the same season. So TN59 doesn't really see that pattern. So therefore, using the same dataset, we added relative humidity to our risk assessment and also look at low temperatures too. And based on temperature and relative humidity levels, indoor conditions were classified into composite risk categories, capturing risks related to high humidity, combined effects of heat and humidity, which is measured by heat index, and also residual cold. So in this graph, we've mapped every single temperature ratings against relative humidity and then classified all 1.6 million ratings into different risk categories. So the percentages you see here are the share of homes that are affected by each type of risk. And hours in the brackets show, on average, how many hours those affected homes spend in that risk zone over the summer. So ideally, we see 100% of homes spending 100% of their time in the green low risk zone. But that's clearly not what's happening here, given that this graph is so colorful. On average, these dwellings spend only about 1/3 of summertime in that low risk zone. More than 90% of dwellings spend on average over 200 hours in hot, humid conditions. And importantly, remember that all of these ratings are summer readings, yet over 70% of homes still experience periods classified as cold or cold humid, which really highlights the dual exposure to both heat and cold within the same season. So when we look at the projections under a high emission scenario, things get much more intense. The caution level hot humid conditions, which is the yellow area, are projected to affect more than 99% of homes, and the average duration roughly doubles to more than 470 hours per summer. And even in this warmest future projection, cold exposure doesn't disappear. It still persists in some homes, which means that dual exposure to heat and cold remains an issue going forward. So to finish, I just want to pull out a few key messages from this work. So first, indoor relative humidity in New Zealand homes is often well above the 40 to 60% optimal band that most overheating standards quietly assume. Comparing the results we got from TN59 and the results based on heat index, if we only look at temperature, we are underestimating risk in humid temperate settings like ours. So second, overheating is already widespread in these low-income homes, and our projections show it gets worse under future warming. High humidity then sits on top of that, amplifying both heat and cold stress and increasing health risks from damp, moldy, in hot, humid conditions. So third, summer isn't just about heat, it's about cold as well, residual cold. Our assessment tools need to reflect that dual risk of heat and cold if we're going to look at summer thermal performance of housing. Finally, the underlying problem is poor quality, low thermal performance housing. These homes don't protect vulnerable households from either heat or cold, as people turn to more active cooling on top of an already long heating season. Our projections suggest that energy poverty is likely to worsen. Historically, household electricity demand has been lower in summer, so summer has worked as a time when hydro lakes can be topped up or at least not drawn down as hard. But heat pump uptake is growing quickly. That means we are no longer talking about a purely winter peak. We're starting to see pressure in both winter and summer. And of course, households who are currently not able to heat their homes properly in winter are also the ones who won't be able to afford cooling in future summers. They are exposed to unhealthy thermal conditions as well as rising energy bills they can't comfortably pay. So from both a housing and energy system perspective, we need housing and energy policies that tackle housing thermal performance, humidity, and affordability together with a clear focus on those already most at risk. So thank you for your attention. So here's my email and LinkedIn. If you have any question or want to discuss more about this work, feel free to connect. Thank you.
Thank you very much. Thank you. That was really insightful, and I loved your diagram with the colours showing the different risks growing over time. Is there a question? We've got about 4 minutes for questions. Yes. Oh, I'll start with you.
Thank you, Vicky White from Brands. Thanks, Zhiting. Really enjoyed your presentation and this research. I was wondering what information you have about the dwellings and whether you've been able to look at the temperatures by different dwelling characteristics at all.
Okay, so you're asking about like the specific dwelling characteristics that might impact the assessment results, right?
Yeah, so like whether you've got information on typology or age, insulation levels. Yeah.
Yeah, unfortunately, I don't really have specific information about each dwelling because that study is based on existing data sets. So rather than develop a single study looking at different dwelling characteristics and how it affects the indoor temperatures, I use the temperature data already collected from different projects and programs, which is quite expensive. So because those programs and projects are so they didn't collect the specific information of each dwelling, and also we have more than 500 dwellings. So I wasn't able to do that, unfortunately, but it's definitely what we wanted to do in the future, especially when it comes to the simulation of different like new technologies or different passive cooling strategies, how it's gonna help with indoor temperatures, and especially how to tackle both heat and cold together. It's definitely what we wanted to look at, like different characters of housing and dwelling. Thank you.
Great. There's one more question down the back here. Which one? Who was it? Here.
When you're looking at the thermal performance of houses, is that just looking at the insulation of the house, or are you also considering things like awnings or verandas that block sun during the hottest part of the day?
Thanks. So, as I just mentioned, I wasn't able to look at the specific characteristics of each dwelling, including their insulation level, their orientation, and whether they have shading in place. So, what we can do, so the aim of this study was just to gain an overview of the thermal risks in those homes using just the temperature data and relative humidity data. So to look at how those how insulation, shading, and other characteristics that may affect the indoor thermal performance. That needs, you need a specific study that designed to collect those data, and because I rely on existing data which didn't collect those specific information, I wasn't able to look at those.